Hi everyone, today a video in the bonding and structure topic looking at ionic, covalent and metallic bonding. So firstly, to look at ionic bonding, metals tend to have 1 to 3 electrons in their outer main levels. We're thinking about metals that are from groups 1, 2 or 3, and the easiest way for them to attain the electron structure of a noble gas, that very stable electron structure of a filled outer shell, 8 electrons, an octet, is to lose those outer electrons, because there's only a couple of them. Non-metals have spaces in their outer level, so typically things from group 7, from group 6, from group 5. These have spaces in their outer levels, and so the easiest way for them to obtain a noble gas configuration is to gain electrons. And so ionic bonding, we say, occurs between metals and non-metals. The electrons are transferred from the metal atoms that lose these excess electrons to the non-metal atoms that have these spaces. And so we end up forming positive and negative ions because we have the metals actually losing their electrons, these non-metals actually gaining the electrons. And for both of these species, they end up forming this noble gas stable electron configuration. So for example, sodium chloride has ionic bonding. The outer electron from sodium's main level, remember that sodium is in group 1, so it has 1 electron in its outer shell. The outer electron from sodium's main level is transferred to the outer level of a chlorine, which being in group 7 has 7 electrons, and so it has 1 space. And so by transferring the 1 from sodium to the outer level of the chlorine, we now have each outer level having 8 electrons, being full. And so both of these elements now have a noble gas configuration of the 8 electrons in their outer main level. And because we've had the actual movement, the actual transfer of electrons, we now have ions being formed. So we've started off with a sodium and a chlorine atom. We've ended up forming a sodium cation and a chloride anion. So the sodium is positive because it's lost an electron. The chloride ion is negative because it has gained an electron. And the two ions, the reason why ionic bonding occurs is because these two ions are attracted to each other by electrostatic attraction between the oppositely charged ions, the positive and the negative charges attracting each other. And so we can say that ionic bonding is the result of electrostatic attraction between oppositely charged ions. And this attraction isn't just necessarily between one sodium cation and one chloride anion, but this attraction extends throughout the compound. And so these ionic compounds exist in a structure that we call a lattice. And so a lattice is shown sort of at the top right here, this kind of infinite extended array of these sodium cations and chloride anions. And here you can see it's drawn out as this cube shape, and it has a definitive number, but in reality these lattices extend kind of infinitely in all directions in 3D. Now, we said that this attraction between the positive and negative ions extends throughout the compound, but there's also repulsive forces, because there's also the repulsive forces of chloride anions being close to each other and sodium cations being close to each other. So the repulsive forces between ions of the same charge, and we have attractive forces between ions of opposite charge. And so when these ionic compounds exist in this lattice structure, these attractive and repulsive forces are balanced between the two. We can also draw out our actual sort of dot and cross diagram almost, which I've shown here in the bottom left. So we start with our sodium atom, we draw. Sometimes it depends on what the question asks. If it wants you to draw out the complete electron configuration, we have to have our first shell with 2 electrons in, then the outer shell after that containing 8 electrons. And then because sodium is in group 1, the furthermost outer shell has 1 electron. The chlorine atom, again, we can draw it out with our 2 electrons to start with, then our 8 in the next shell, and then the shell after that will have 7 because it's in group 7. Sometimes you can simply show it as just the outer level, just the valence electrons, the ones that are actually really important in this. And so the sodium would just have 1 electron, the chlorine atom would just have 7. And then we can have our transfer. Here it's shown by actually showing this arrow, but another way is to do a dot and cross diagram, so to show the sodium electrons as being dots, the chlorine atom electrons as being crosses. And then we end up with our sodium cation, where we've lost that electron and gone down to the previous level that has 8, that noble gas configuration. And the chloride anion that we produce now has gained the electron, and so we have an outer shell here with 8 electrons as well. But the key thing is that it is electrostatic attraction between oppositely charged ions. Lots more examples on this page. Again, the key thing here is that we're always going to have some form of metal with a couple of valence electrons to get rid of, such as the one for the sodium or two for magnesium. And we're going to have a non-metal which has a couple of spaces. And the easiest way is for the metal to lose a couple of electrons, the non-metal to gain those electrons. And we always generate these ions. So we can have a look here at magnesium oxide. Magnesium is in group 2, so it has 2 valence electrons in the outer shell. The easiest way that it can obtain a noble gas configuration is to lose those 2 electrons. Our oxygen atom has 6 electrons, it's in group 6, so it has 2 spaces. And so the easiest way here is to take the 2 electrons from the magnesium and transfer them to the oxygen. That then leaves our magnesium having a full octet, a stable electron configuration, a noble gas configuration. And our oxygen, having gained these 2 electrons, becomes again a stable noble gas electron configuration. And so we end up with a magnesium 2+ cation and an oxide O2- anion. And again, it's these strong electrostatic forces of attraction between oppositely charged ions that forms the ionic bond. Another example could be magnesium chloride. This is where we have to be a little careful with the formulas of our compounds. So magnesium chloride, magnesium again has the 2 electrons, so we know that it's going to give up those 2 electrons, form an Mg2+ cation. Our chlorine though is in group 7, so it has 7 outer electrons, and therefore it's only got space for 1. And so in order to get rid of the 2 electrons from the magnesium, it has to give those to 2 separate chlorine atoms, each chlorine atom accepting 1 of those electrons. And so 1 electron each from the magnesium goes to 1 of the chlorines, and so that leaves us with our Mg2+ cation, which would have a full, here it's been shown as just having an empty outer shell, but in reality that shell essentially then goes down 1 to the 8 electrons in the previous shell, that noble gas stable configuration. And our chlorines have now become chloride anions, Cl-, because they've gained an electron each to have that full octet. And finally, calcium oxide, very similar to the magnesium oxide. The calcium is in group 2, so 2 electrons in its outer shell. The oxygen in group 6, so it has 6 electrons in its outer shell. The easiest way for this to obtain the noble gas configurations is for the calcium to lose 2 electrons and for them to be picked up from the oxygen atom. And so here you can see these actual dot and cross diagrams drawn out, where we're showing the crosses on the calcium, the dots on the oxygen, and that ends up forming a calcium 2+ cation that has the stable electron configuration with 8 electrons in the shell below. And we have our oxygen here becoming an oxide anion, O2-, because it's gained those 2 electrons. We've got 2 crosses in there as well as the dots. So ionic compounds are nearly always solids at room temperature. They have these giant lattice structures, and therefore they have really high melting points because they need a very large amount of energy put in to melt the compound by breaking up this infinite lattice of ions. We have to actually break the electrostatic attraction in 3 dimensions, in all sort of extending out in all directions. So a lot of energy needs to be put in order to melt the compound. Now, ionic compounds conduct electricity when they are molten or dissolved in water, something that we call aqueous. The key thing is they do not conduct when they are solid. And the reason for this is because for them to be able to conduct, we have to have charged ions, which we do in both the solid and liquid state. But these ions have to be able to move. To be able to conduct, we have to have these ions being able to move and to carry the current, the flow of charge. And so in the liquid state, they are free to move. In the solid state, they are stuck in this rigid infinite lattice. And so they're not free to move, and therefore they don't conduct in the solid state. Ionic compounds are also quite brittle and shatter easily. This is because we have this lattice structure of alternating positive and negative ions. If, for example, I am to hit this lattice structure in a given direction, this may move the ions, and so rather than having this nice kind of normal negative, positive, all layered kind of on top of each other where negative and positives are always in contact, we never have any negative and positive directly in contact. What it can actually do, by knocking it in one direction, it causes a displacement of essentially a layer of this lattice, such that it might put negative charges on top of each other. That's very, very repulsive, and so the lattice breaks up. because we have this repulsive force between ions of the same charge. And so the key thing is they're brittle and shatter easily, and they conduct electricity when either molten or dissolved in water, essentially in the liquid state, but not in the solid state. Then we can start to look at covalent bonding. So a non-metal needs to receive electrons to fill the spaces in the outer shells. We said that when we talked about ionic bonding. But a covalent bond is formed between a pair of non-metal atoms. Now in this case, it's just not energetically favourable for one of these non-metals to lose all of its electrons and the other to gain it. It's much more favourable for them to just share some of their outer electrons. So rather than formally losing and gaining them, they're just going to share them, so that each atom obtains this stable noble gas arrangement. And so a covalent bond is a shared pair of electrons. A covalent bond is always 2 electrons, at least. Now, if we have a small group of covalently bonded atoms, this is called a molecule. And the atoms with covalent bonds are also held together by electrostatic forces. The electrostatic forces are between the electrons and the nuclei of the different atoms. Essentially, the electrons you can think of as being the glue between all the different atoms. And this takes place within the molecule. And the simplest example of a covalent bond is the hydrogen molecule, which is simply 2 protons held together by 2 electrons. If we think about a hydrogen atom, 1 proton, 1 electron, and so a hydrogen-hydrogen covalent bond, the hydrogen molecule H2, essentially is 2 protons held together by 2 electrons. And so the attractive forces between the electrons and the nuclei, those oppositely charged electrostatic attractions, just balance out the repulsive forces between the like charges when the nuclei are a certain distance apart. So by bringing them closer together, we get the repulsion of the 2 protons essentially, but we also have the attraction of these electron-proton interactions. And so there's lots of examples on this slide of these covalent molecules. We have methane, ammonia, water. These are all examples of covalently bonded molecules. In the methane, for example, we have a carbon, 4 electrons, a bit too many to just lose 4 electrons. But we can share these 4 electrons with 4 hydrogen atoms, each of which has 1 electron. And by doing that, each hydrogen atom now has 2 electrons, and the carbon atom has 8 electrons. And so we can see we've drawn this out as our dotted cross diagram. Ammonia, also similar. Our nitrogen, our central nitrogen here has 5 electrons. It's in group 5. Again, too many to lose. And in this case, we're going to form the 8 electron noble gas stable configuration by sharing 3 of these with hydrogen atoms. And so by sharing the 3 hydrogen atoms, the nitrogen now has 8 electrons. It has the 6 that are in these covalent bonds and 2 as a lone pair. And each hydrogen atom has 2 electrons. And then finally water. Oxygen's in group 6, so it has 6 electrons. It needs 2, and so it can form these 2 covalent bonds to hydrogen atoms by sharing 2 electrons, and it achieves this stable 8 electron noble gas configuration. Each hydrogen has 2 electrons. The oxygen now has 2 covalent bonds, so 4 electrons in covalent bonds being shared, and 4 electrons as lone pairs. We've looked at the hydrogen atom example. Another example would be 2 fluorine atoms coming together to make F2. Here, each fluorine atom has 7 electrons. The easiest way for this to achieve a noble gas, rather than losing one of them and then having one with 8 electrons but leaving one having only 6, the easiest way is for the 2 fluorine atoms to actually share an electron each. And so this kind of normal covalent bonds is where we have 1 electron from each atom coming together to be shared. So 1 from the first fluorine, 1 from the second fluorine. They share it, and therefore by doing that, each of those atoms now has 8 valence electrons. So that's stable noble gas configuration. Carbon dioxide is another example. And so here we have our carbon atom with 4 electrons, our oxygen atom that has 6. Now actually this one might seem a little bit more difficult to work the numbers out, but actually the way this can happen is if each of our oxygens shares 2, if we have 2 oxygen atoms and each one shares 2 electrons with the carbon atom. The carbon atom needs to have 4 electrons. Now rather than sharing, just having 1 oxygen atom and sharing 4 of the electrons from our that 1 oxygen atom, what we do is we share 2 electrons from 2 oxygen atoms. And so if we share 1 electron, like we saw in the fluorine or the hydrogen or the methane, the ammonia, the water examples, 1 from each, we have this single covalent bond. Because we're now sharing 2 electrons from our oxygens, these are examples of double bonds. So the carbon dioxide is C double bonded to oxygens. And so by doing this, by sharing 2 electrons from our oxygen atoms, our oxygens now each have 8 electrons. They have the 6 they started with, plus 2 that are being shared from the carbon. And the carbon also has 8 electrons because it has the 4 it started with, plus the 2 from each oxygen atom that is being shared, so overall 8. And then finally, another example very similar to the methane is carbon tetrafluoride, CF4. Here, instead of having 4 hydrogen atoms, we have 4 fluorine atoms and a carbon atom. And again, the easiest way for this to obtain the right configuration, those 8 electrons in the outer shell, is for each fluorine to share 1 electron, so a single covalent bond, with the carbon. So each fluorine now has 1 shared from the carbon, and so each one of those has 8 electrons, and the carbon has the 4 it starts with, and the 4 that are being shared from from the 4 fluorines, to make 8 electrons there as well. Now, as we just said, a double bond has 4 electrons being shared. We can go even further, up to a triple bond, which has 6 electrons being shared. And this is always to achieve a noble gas electron configuration, the 8 outer electrons. Now, all the examples that I've shown on this slide here are neutral molecules. The atoms within the molecules are strongly bonded together with covalent bonds within the molecule. So the bonds between the actual atoms, between the C's and the H's, the C's and the O's, the 2 N's at the bottom, those bonds are very strong covalent bonds. However, the actual molecules, so for example, if I take the top example, there I have 1 molecule of CO2. The molecule is held together very, very strongly. The atoms within the molecule are held together very, very strongly by those covalent bonds. Molecules of CO2, though, are not strongly attracted to each other. So we say that we have very strong intramolecular, within the same molecule, forces, but very weak intermolecular forces. So weak being, intermolecular being in between molecules. So strong intramolecular forces, those actual covalent bonds, weak intermolecular forces, the forces that happen to act between the molecules. And so we can see here we have some examples of double and triple bonds. So we have the double bonds that occur in CO2. So we have 4 electrons from carbon. The oxygen's having 6 electrons. The only way this can achieve the noble gas configuration here, in this case, is for the oxygens to share 2 of their electrons rather than just sharing 1. And so we share these 2 electrons from the oxygen, each of those to the carbon. The carbon has 8, the oxygens have 8. Second one down is a molecule of an alkene called ethene. So this has a carbon-carbon double bond. And you can see here that we have our carbons here sharing 1 electron with hydrogen atoms. There's 4 hydrogen atoms. And so by doing those 2 hydrogen atoms, we have the 4 that are already on the carbon, the 2 that are being shared from the hydrogen atoms to make 6. And so the only way to get up to 8 is for it to share 2 electrons each with each other. And so we have these 4 electrons essentially being shared, 2 from each, and that creates our double bond. And then finally, nitrogen down at the bottom, N2. This is one of the strongest bonds that are known, certainly the strongest bond between 2 of the same element, because it's a triple bond. So triple bonds are stronger than double, and they're stronger than single bonds. And so here, nitrogen has 5 electrons. The only way this can actually achieve our noble gas configuration of 8 electrons is for each to share 3 of these. And then each nitrogen has 8 electrons because there are 6 being shared in the middle, and then 2 that are not being used on each atom. Now, substances composed of molecules are gases, liquids or solids that have low melting points. The strong covalent bonds that we talked about between the atoms within the molecule, these strong covalent bonds are only acting within the molecule. Now, when we melt something, we're not actually breaking these actual individual covalent bonds between the atoms. We are breaking the intermolecular forces, the forces that act between molecules. And because there's only a weak attraction between the molecules, therefore there's only a small input of energy needed to break them and move them apart and to melt them or to boil them. Now, covalent substances are poor conductors of electricity because these molecules are neutral overall, and therefore they can't carry any current. There's no charged species in any of these examples here, and so typically covalent substances are very poor conductors of electricity. While these ions may be able to move as a gas or a liquid, they can't carry charge. If they dissolve in water, they don't break up into constituent ions because they weren't formed from ions, they were formed from essentially neutral atoms sharing electrons. And so if they dissolve in water, they remain as molecules. The solutions do not conduct electricity. So one way you can tell the difference between an ionic and a covalent bonding in a molecule is if it conducts electricity. If it does, it's likely ionic. If it doesn't, it's likely covalent. There are no charged particles here to be able to carry charge and conduct electricity. Now, another type of covalent bond is something called a coordinate bond or a dative covalent bond. Now, in a single covalent bond, we have a pair of electrons shared between two atoms. And in most covalent bonds, kind of a normal covalent bond, each atom provides one of those electrons. Think about H2 or F2. We have one electron from each atom being shared. It's a very mutual sharing, one electron from each. In some bonds, though, one atom provides both of the electrons. So rather than having one electron from atom A, one electron from atom B, both electrons come from one of the atoms. And this is called coordinate bonding or dative covalent bonding. So the atom that accepts the electron pair will be an atom that does not have a filled outer main level of electrons. It will be something that is electron deficient. The atom that is donating the electrons will have a lone pair of electrons that is not being used in a bond, an actual lone pair. And so the key thing here is that we can form a covalent bond for sharing of electrons, but we can't do it in the normal fashion because one of these species, the one that is electron deficient, doesn't have any electrons left. It can't use one of them to form a covalent bond. And so the only way this can form a covalent bond is for the other partner to donate both of its electrons. So a coordinate bond is both electrons from one of the atoms. And we represent coordinate bonds by representing an arrow. Now sometimes this won't, in all cases, always be shown, but really if we're doing it for A-level, we should show it with an arrow. And this just indicates to us that we have both electrons here being donated. And this bond in reality is actually no different to any other bond. It's just to show that it was made differently from the donation of both electrons as opposed to just the sharing of one. And so these covalent bonds will have the same strength, the same length, for example. It's just that we're showing that it's made differently. It's kind of to remind you that it's a coordinate bond and not a normal covalent bond. Now, we can look at some examples here. So the first one is creating the ammonium ion, NH4+. We do this from an ammonia molecule, NH3. This has a lone pair of electrons. It's a covalently bonded molecule, a nitrogen having 5, each hydrogen having 1. The nitrogen shares 3 of its electrons, 1 each to the hydrogens, to create 8 electrons to the nitrogen and 2 electrons each for the hydrogen. And we also make this then by reacting it with a hydrogen ion, a hydrogen cation, H+. This doesn't have any electrons. Think about the normal hydrogen nucleus, 1 electron, 1 proton. H+, we've kicked off the electron and therefore we are left with no electrons. The only way that the covalent bond can happen here is if the nitrogen donates both of its electrons to that hydrogen ion. And so by doing that we have NH3 plus H+. This forms NH4+. So one way just to double check you got it right is to make sure the atoms and the charges balance. NH3 plus H+ must give us NH4+. And you can see there that it's been drawn as an arrow from that lone pair to the hydrogen. And then there's a kind of bracket at the top to denote that the whole molecule has a positive charge. And note that this ammonium ion is a charged particle, but it was made from covalently bonded atoms. So while it's charged, we might think potentially it's ionic. It was made from covalently bonded atoms. Another example is something called the oxonium ion, again a charged particle, this H3O+, but it's again made from covalently bonded atoms. Here we have a water molecule, H2O, and we have a proton, H+. Again, the only way this can make this covalent bond is by both electrons from the oxygen donating, being shared to the proton, which has no electrons. And then finally, another example here would be an ammonia molecule, NH3, reacting with BF Now, BF3 is electron deficient. Think about where boron is. It's in group 3, has 3 electrons. Each fluorine in these covalent bonds is shared with 1 electron. So we have 1 electron from each fluorine, 3 from the boron, 6 electrons on our boron. But then that's it. That's all the electrons we have, just 6 valence electrons. So there's actually an empty p orbital on our boron. So it's electron deficient. We have an ammonia molecule that has a lone pair. And so we can form this covalent bond. And so again, you can see here that we have this. Here they've actually just drawn it as a normal covalent bond, but actually it is a dative covalent bond. And again, just make sure that your atoms and charges balance. We started off with 2 neutral molecules. We must end up with an overall neutral molecule, therefore. And you can see here that the boron now has a negative charge, the nitrogen has a positive charge, because we've made 4 bonds to the boron and 4 bonds to the nitrogen, but we've used the electrons from the nitrogen. So it's positively charged on the nitrogen, negatively charged on the boron. And this example here is something we call a Lewis acid-base pair. We can define Lewis acids bases in other videos. I won't do it here. If you want to go and look at my transition metal series, I'll talk through Lewis acids and bases, but this is what we call a Lewis acid and base adduct. Essentially, one of them has a lone pair, one of them is electron deficient, and so this coordinate bond is formed, and it's called a Lewis acid base adduct. Then finally, we can look at metallic bonding. So metals are shiny elements that are made up of atoms that can easily lose up to 3 outer electrons. We said for ionic bonding, metals tend to have 1 to 3 electrons, and they lose those is the easiest way to get to the stable electron configuration of 8 electrons in the outer shell. And so these metals can very easily lose their outer electrons and leave positive metal ions. Now, the atoms in a metal can't transfer the electrons like in an ionic bond unless there is a non-metal element present. So, for example, in sodium chloride, the sodium can lose its electron to form sodium plus, and this can only happen because there is a chlorine around that can accept that electron. If we just have sodium metal, we can lose our sodium, we can lose our electron, but where does the electron go? It can't be accepted by another sodium atom. That will also be losing electrons. So in a metal element, the outer main levels of the atoms all merge together. And so these electrons, these outer electrons, are actually no longer associated with a particular atom, with a specific metal atom. And so we use the word delocalized. We say that there is a delocalized sea of electrons. And this is used to describe where we have these electron clouds that are spread over more than 2 atoms. They're not localized on an atom, they are spread out over a number of atoms. They are delocalized. And so in metallic bonding, there is a lattice of positively charged ions existing in a sea of delocalized electrons. So again, we have this lattice structure, this infinite kind of 3D array of our metal ions. The positive ions tend to repel each other because they are of the same charge, they have repulsion, but this is balanced by the electrostatic attraction of these ions with the sea of delocalized electrons, that positive-negative electrostatic attraction. Now, the number of delocalized electrons depends on how many electrons have been lost by each metal atom. So, for example, in a sodium metal, there is less delocalized electrons than there is in a magnesium metal, because we have 2 electrons being lost from magnesium versus 1 being lost from the sodium. And again, this metallic bonding extends infinitely throughout the structure, and so metals have what we call giant lattice structures as well, like ionic bonding. And so if we're drawing some sort of schematic diagram, typically we show this kind of the lattice of positive ions, this regular array of positive ions, all sort of spaced equally. And then in between them, we show the electrons, and typically make sure we show enough electrons that they should be. But typically the key thing is that they are delocalized. They don't actually still exist on one particular atom. They move all around all of the different ions. Now, if we think about the properties of metals, metals are good conductors of electricity and heat. The delocalized electrons that we have in our metal can move freely throughout the structure. Because they're delocalized, they're not stuck to a particular atom or associated really with a particular ion. They can move freely around the structure. And so an electron from, if we connect this up in terms of electricity, an electron from the negative terminal of the supply can join the electron sea at one end of a metal wire, while at the same time a different electron leaves the wire at the positive terminal. Metals are also good conductors of heat. They have high thermal conductivities, And the reason for this is because our sea of electrons allows energy to be spread by increasingly vigorous vibrations of these closely packed ions. So because these ions are all quite closely packed and rigid, they can vibrate very easily, and therefore they can transfer energy and transfer this heat. Now, when we think about the strength of metals, the strength of the metallic bond depends on two main factors. The first is the charge on the ion. The greater the charge of the ion, for example, a Mg2 plus versus a sodium plus, or a aluminium 3 plus versus a sodium plus, the greater the charge, the greater the number of delocalized electrons there will be, and therefore the stronger the electrostatic attraction there is between the positive ions and the electrons. There's greater electrostatic attraction simply because we have higher charged ions and more electrons. And so that's what we're really considering for the strength of this metallic bond. The other one is the size of the ion. If the ion is smaller, that positive metal ion, well, the closer the electrons can get to it, and therefore the closer the electrons can get to the positive nuclei, and hence the stronger the bond is. Metals are also malleable and ductile. So meaning malleable means they can be beaten into a certain shape. Ductile means they can be pulled into thin wires. Now, after a small distortion, remember for the ionic bonding, if we kind of hit the lattice in one direction, this often meant the lattice shattered and broke apart. They were very brittle, because it quite often meant that rather than having sort of positive on top of a negative on top of a positive and those attractions, we might knock it in such a way that we now have a series of positive ions all stacked on top of each other. That's repulsive, it's brittle, it breaks apart. For metals though, because we only have positive ions, after a small distortion, technically each metal is still in exactly the same environment as it was before. And so this new shape is retained as opposed to being broken apart. And metals also have very high melting and boiling points because they have these giant structures, these giant lattices that extend infinitely in 3 dimensions. There's really strong attraction between the metal ions and the delocalized sea of electrons, and it makes the atoms very, very difficult to separate. We have to put lots and lots of energy in to separate it, and hence they have very high melting points. So, time to have a go at some questions. If you'd like to have a go, pause the video, and the answers will be on the next slide. So the first question was asking us what type of bonding was present in AlCl3 and to draw a dot and cross diagram. So here we have a metal, aluminium, with 3 electrons, so it's going to be able to lose those 3 electrons. We have chlorine, which is a non-metal with 1 space, and only has 7 electrons, and so this can accept electrons. And so this is ionic bonding, this strong electrostatic attraction between oppositely charged ions. And so if we draw our dot and cross diagram, I'm going to draw my 3 electrons as dots on the aluminium, my 7 electrons in the outer shell on the chlorine as the crosses. And then because we're losing 3 from the aluminium, but the chlorine can only pick up 1, we need 3 chlorines to be able to kind of mop up all those electrons that the aluminium is losing. And so in doing that, we end up with our aluminium. Now you can either show it as a sort of an empty outer shell because it's lost those 3, or you can show it as being the shell below now, which is full, which would have 8 electrons, that stable noble gas configuration. And then our chlorine has accepted one of those electrons, so we have our 7 crosses and then 1 dot. We have to put 3 in front of it because, of course, we have 3 chlorine atoms that we started with. And so we end up making this aluminium 3 plus cation and 3 lots of the chloride anion. Second question here is to do with the type of bonding present in oxygen, dioxygen, O2. Here we have 2 non-metals, and so the only way this can attain it, rather than losing 6 electrons each and messing about like that, instead it's going to just share electrons. So this is a covalent bonding present here, the sharing of electrons. And the only way that this can achieve it is if we actually share 2 electrons each. So we form a double bond. We have 4 electrons being shared in total, so a double bond. So each oxygen has 6 electrons. You can imagine if we shared just 1 of those electrons each, that would only end up then having 7 electrons in each oxygen. And so by sharing 2 electrons from each oxygen, each oxygen now has 8 electrons. We have the 6, for example, the 6 crosses on the left oxygen, plus the 2 dots that are being shared from the other to give 8. And likewise for the other oxygen, we have 6 dots plus the 2 crosses that are being shared. So we have 8 electrons on each, that's stable noble gas configuration, and we have technically an oxygen-oxygen double bond because we have 4 electrons being shared. Question 3 was to ask which has the higher metallic bonding strength, sodium or magnesium. Well, remember that the two things that dictate the metallic bonding strength was the size of the ion and the charge on the ion. Magnesium is obviously a 2+ ion compared to a 1+ ion for sodium, and so there's much greater electrostatic attraction between the nuclei and the sea of delocalized electrons, and so therefore the magnesium has a higher metallic bonding strength than the sodium. It's because of that greater electrostatic attraction between the positively charged nuclei and the sea of delocalized electrons. Question 4 was then which has the higher metallic bonding strength, sodium or rubidium. Now sodium and rubidium are both in group 1, so they're both +1 ions, so it's not the charge that we're looking at here, but actually the size of the ions. Sodium is a smaller ion because it's only in period 3, as opposed to rubidium, which is in period 5, a much bigger ion. And so the sodium actually has the higher metallic bonding strength because the nuclei are smaller essentially. The ionic radius is smaller, and so our nuclei are closer to the sea of delocalized electrons. And when we think about electrostatic attraction, the closer things get, the stronger that attraction is. If we want to look at it in a more advanced way, of course, we think of electrons not really as being these dots and crosses, but actually being as diffuse, as being electron clouds, these regions of negative charge in these electron clouds. The bigger the ion is, the more diffuse, the more bigger these electron clouds are, and therefore they overlap less effectively with the metal nuclei. But another way to say it is to simply say that the sodium is smaller, and therefore the nuclei can get closer to the sea of delocalized electrons. If ions can get closer to each other, that's stronger electrostatic attraction. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.